I'm recording.
All right. So
All right.
when we look at this assignment, we are required to assess the likelihood of safely advancing 3-section continuum robot with follow the leader motion in lung airways of patients. The robot is 3-section robot with each section 10 millimeters long. No trunk is attached to the 3-section robot, only 3-section, 3-car train-like robot, advanced in the lung way. Here safely should be measured proximity to the airway wall or collision to the airway wall. Also, definition of assessment and likelihood shall be defined by the team and approved by Dr. Hatt. Okay. So I think the first thing we need to do is understand what will be the kinematic equations that we will use for that.
Right. So I started playing with the information Dr. Hatta provided. There's some lecture data, and I'm gonna highlight here real quick. I'm gonna go to assignment. Through the modules.
Yeah, I'm just thinking if we're gonna do it with the GH parameters, or I know David had an equation, a different method of finding the reference points with an equation instead of a GH parameter table. So I would really like to do it both ways and see what happens.
Yeah, I kind of started to work on this briefly. So there's in the modules, he expressed this paper regarding or some suggestions regarding two-dimensional lung airway map. So he is expecting us to use these pictures, these images, and make the robot go through this aperture. He also gave us the amount of the space for this. So I kind of took a step back to this application and kind of wanted to do the same as it was the previous work with the fast planning homework. So if we could use the random tree analysis to identify the walls of these channels and then do a path internally.
No, that's fine, but you have a problem here that I agree with you through all of this and doing the RRT and defining the path. That's great. But this path, are you recording?
Yes.
Okay, but this path is the path of a point. Now we need to do the path of the continuum robot itself.
Right.
Which will
so
be
we need to
yes.
we need to add some rigid body tree into this, which is the point where I am at right now. So I'm just gonna show you. Oh, what happened here? Oh, let me look for the. Let me look for the file real quick. Okay. You see my screen again?
Yes.
It is running very slowly, but so going through the process that he already showed us how to do, importing the image, and then
Which is what
using
we did
the
for last assignment.
correct, yeah, no, nothing different. Very same approach, different picture.
Yeah.
I just did, I did change the size. I compressed the image a little bit
Yeah.
to meet the dimensions he was talking about
Yeah.
in the. So again, you can see here the random tree, the end position or end goal, and the path for one dot or one end effector going through the entire robot using the random tree.
Yes.
So now I was doing some research to how we could then add a manipulator using the robotics toolbox to the actual state validation, which let me go up. Yeah, to the here you go. So to the validation state or validator occupancy map, um, based on I was looking for different examples, Rami. I start playing with it. Let me see. Oh, here you go. So in this example, they create a 6 degree of freedom robot, which starts at the bottom of the floor and then avoids colliding with this table, going through the back and picking this item from over the table. So looking at the code and how they do it, they do the collision box as we were doing in the previous assignment, um, and they also created a state space like the one we use for the mobile robot. Um, so, and they also on the validation state, they also add the where is it? They also add here the end effector and the base frame of the rigid body tree, and the rest of the code, even though there's some example functions which I don't understand just yet, at the end it is very similar to what we did, um, and he does here some additional simulation. So if we run it, I'm not going to run it because it's very slow. If we run it, it will start like down here and it will go up, 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 avoid colliding, and then picking the red cylinder.
I
So
think that is, yeah.
I was looking for something more similar where we could import an image and then use the DH head parameter we already have as a it's not a steady state, it's a
So let me,
yeah, go ahead.
no, I think this is a good idea, but I'll share to me, this is 3D and we're still trying to do it in 2D. So I think that's good, but I'll share with you my thought. I have another idea. Can you
Okay.
open can you open your previous work, your previous MATLAB project, MATLAB code that you showed the
Oh, you want me to still share?
yeah,
Okay.
share your code, and I'll think with you in a loud voice here.
Okay.
So what I'm thinking, okay, perfect. So first, a couple of things. Let's go to the map where you already have the path drawn into it. So where you have the RRT ran and you have, yes, this one, great. So I think the very first step we need to do is to figure a method to smoothen that path. So because when you have a manipulator in there, and if it's gonna follow that path, it will stick out from every side of the bronchi. So you need to we need to smoothen that path first. I think that's the first thing, is to smoothen the path.
Right.
So we'll have to look for smoothing algorithms, and I found you can actually do that by changing the value of your validation distance. Yes, that makes a difference in
So
how
what do you want me to use? 1?
So that might be too much. Try it, see what you get.
All right.
But there might be other methods of smoothing the path. There might be a function for smoothing that we can integrate, and that's what I'm looking for. I'll research this tonight and see if I can get to that.
Perfect.
So that's something I want to research on my own. And you can research too, because I don't think just by changing the validation will take care of it. We have to do, there should be a smoothing function or something. So let me look into that. And then the other thing is,
It did got better though. So
it
if
did,
we were to increase the, if I increase it a little bit more, what's the outcome of that?
yeah, and it might work. I just want to see if there's another.
No.
It still comes too close to the edge in certain locations. So,
Yeah.
well, this is something we can do. The next step is, let's see here, where in the code do we show the actual point that we're navigating? Where is that point in the code here?
The navigation locate position.
Yeah, the position of the red dot as it moves.
Oh, the red dot would be
Solution info,
uh,
right?
yeah, the object. So it will be the left side, the left object once you create the planner. The one on the
Yeah.
left is the actual route that robot will follow.
So that's where so what I'm thinking is, we need
That's
to
the
do it in
trajectory we need to give. That's the waypoint we need to give to the robot.
exactly.
All right.
So that's one way of looking at it. The other thing is, what we need to do is, it's a 3-section continuum robot. So when we do the DH parameters, we need to be able to find the location of the first point and of the second joint and of the first joint. So first, second, and third joints. So basically we're not tracking 1 point, we are tracking 3 points at a time. You see what I mean?
Right. I see what you mean.
Or what I'm trying to say. is that you have 3 points that you are tracking and making sure that you are in there. So what I think I have an idea of what I want to do or how I want to do that. So I'm trying to.
I'm gonna send you. I'm gonna post this code in the discussion,
Yeah.
so that you can pull it up and don't spend too much time on what we already have. And then so the actions would be to find a way to smoothen the path. But he also mentions that so if we create a path to follow, let me think this, get this straight. So we're just analyzing an area beforehand, and then we're gonna send the robot in through a specified path. That's it. That's all we need to do.
Yes. Yes. So
And
I'm thinking. Here is my thought. We smoothen the path. We find a way to smoothen the path, and we run the RRT algorithm, and then we come up with a straight line, a nice curvature path through from start position to end position. This path that we will create will be made up of, I don't know, 500 points, 300 points, whatever the number of points it's made of. These points, we are going to feed it as inverse kinematics to the snake robot. And then at each point, it will determine the position of each bend, and then we can do forward kinematics on the first and second joints, and this way we are plotting the location of the first joint of the end effector joint, which should follow the path, and then we are plotting the location of the second joint and third joint. So we will have the path that's created by the RRT, and then we will have 3 lines connected that will go in there, and it will keep moving, and this will be the actual robot path. And then we will find the difference between the theoretical path and the actual one of the snake robot of each of the 3 joints. Does that make any sense? I lost you. You're muted.
yes, it does make sense.
It might, I don't know if it's too complicated, but basically the idea is we use, once we get the points, we use inverse kinematics to determine the angles of the robot of each joint for the end effector at this point to get there. And then once we have those values, we use forward kinematics for the first and second joints to be able to see where they will sit. And then this way we will have 3 points for every point on the original trajectory. We will have 3 points that we generate. And then we just connect we put all of that in an array, and then we plot. So we will have the red line could be your theoretical path, and your blue line could be your actual path. The only other thing that we will need to do is figure a way to, because you will have 2 arrays that are different sizes. So your red path will be like your 300 points, but your blue path, which is the location of each of the end effector points at every location will be 900 points, for example. So that's 300, that's 900. How are you going to match them? So unless you do some interpolation between or something, that you can subtract both from each other, do a standard deviation. We'll have to think on that part of it.
Right. I believe this planner already does that for you. Where is it? So the planner, it does exactly that. It goes through the connected tree only because the tree has a lot more points or waypoints, but this planner will give you the waypoints that connect you to the end goal. So I believe that is already happening, or a portion of what you're saying is already happening here.
But we have to do all of this for the snake robot.
Right, right. So, yeah, it's tough. So I believe the approach that I am going to follow now, like you said, I'm gonna use the actual path trajectory, like even though it's not perfect, I'm not straight in the middle, but I can make the robot, I can create a trajectory using the task planner or the joint, what was it, the space, joint space or task space planning,
I just
following
got an
this,
sorry, I don't
using these specific waypoints. That is one approach we can take. What are you thinking?
So I just got an idea I want to share with you. So go back to the picture of the trachea. Yeah. So right here. So one thing we can do, and I don't know if that's okay or that's considered, but it's an idea that I just thought of. So right now we have all those white sections. So what we can do is we can actually add two black lines as obstacles. So basically we're forcing that path not to use all of that space. But I don't know if that is.
Yeah. I see what you mean. There's a function for that. There's a function to allow. How can I say this? There's a portion to specify a function to specify that the random tree needs to be farther away from the corners. So that would be what we need. That's what we need to do, is so that we are closer to the center.
Exactly. And this will straighten it by itself. So that will take care of that part.
Let me, I know I saw it on one of the examples, so I'm gonna look for that. I believe it's kind of it's an offset, or exactly like a limit offset.
Yes.
I'm gonna look for that.
So if we do that, that should smoothen the path better and center
Right.
it in the middle. Once that is done, then I can start to work on the inverse kinematics and forward kinematics of the snake robot.
All right. So I'm gonna share this. Let me. Okay. And then I'm gonna upload it in 1 second. I am uploading it. Oh, so Dr. Hatta just sent me an email. Let me see what he said.
And we need to tell him, we need to speak to him about having a meeting on this snake robot project and discuss our plan of attack and see his thoughts.
So Dr. Hatta said, I'm driving now. I just found it and I'm driving now. What should we do?
So can you send him an email and say, ask him if he would be available later today?
Okay, I'm gonna stop recording. That's okay?
Yeah, it's fine.